Good morning. Our topic for this morning is the barrier potential and temperature. Is there a relationship between the change in temperature of the junction temperature with respect to its barrier potential? So, let's check their relationship. So, it says here that there is a rule for estimating the change of barrier potential and what affects the barrier potential of our silicon diode. So we are talking about silicon diode. So what affects the barrier potential? It is actually the increase in temperature. If there is a rise of temperature, a degree rise of temperature, there is a decrease of 2 millivolts for each degree rise of temperature. So, expressing it mathematically, we have this one. The change of voltage with respect to change in temperature is simply equal to negative 2 millivolt per degree Celsius. Meaning to say, if there is an increase per degree Celsius in our junction temperature, there will be a decrease. That's the reason we have the negative here. There will be a decrease of 2 millivolts. Meaning to say, if it is not a rise of temperature, there will be an increase of voltage. So, the other way around. So, rearranging now this formula, what we have is the delta T will be multiplied with this quantity. So, for that reason, we have now delta T multiplied with the quantity negative 2 millivolt per degrees Celsius. So, for us to know how will it affect the junction or the barrier potential with the change in junction temperature, let us now solve this example. So, we have now a barrier potential which is 0.7 volts. So, particularly, this is now a silicon diode. Okay? So, the ambient temperature, so this is now your initial temperature or T sub I, is simply 25 degrees Celsius. So, it says here we are asked to solve for the barrier potential of the diode when, letter A, the temperature increases to 100 degrees Celsius. And, letter B, okay, when the temperature decreases, okay, or it becomes 0 degrees. So, let's now proceed. Okay, so, we have now, let's now proceed. What are the given? Okay, that's the given now is we have the barrier potential of the diode. Initially, it's 0.7 volts. Okay, at the ambient temperature of what? At 25 degrees Celsius. But now, for this example, we are now required to have the actual barrier potential when the temperature increases to 100 degrees Celsius, and what is the barrier potential of the diode when the temperature decreases to 0 degrees Celsius. So let's have the solution for this. As mentioned in our discussion, the change in voltage is simply equal to negative 2 millivolt. There will be a decrease of 2 millivolt per degree Celsius if there is a rise in temperature. So, delta T is simply final minus initial. So, this 100 degrees Celsius is now our final temperature. Okay. So, we have now delta T is final minus initial. So, 100 degrees Celsius or 100 minus 25 degrees Celsius, factor out. So, the degrees Celsius and degrees Celsius will cancel out, leaving us now a value of what? So, 100 minus 25 is 75, okay? So, 75 times 2 millivolts will simply gives us a negative 150 millivolts, or mathematically, this is simply equal to negative 0.15 volts. Okay? Is this already the barrier potential? No, that is just the change happen when your temperature increases to 100 degrees Celsius. So, what is now your barrier potential? So, your barrier potential now is simply equal to the original, 0.7 volts. Then, add now the change in temperature, which is simply equal to negative change of voltage, which is now simply equal to negative 0.15 volts. So this becomes 0.7 volts. So we have now 0.7 volts minus 0.15, and that will give us a value of 0.55 volts. So what did you observe? What we have observed is the barrier potential from 0.7 volts, it decreases to 0.55. What is the reason? It's because your temperature increases. Alright? So that is the principle that was discussed before we solve this problem. Now, that is now the solution for letter A. Now, let's proceed with our solution for letter B. So, for letter B, this time, let's check what is the change in voltage. So, the formula is the change in voltage will have a decrease of negative 2 millivolts per degree Celsius. And what is now the change of temperature? So, for letter B, this becomes now our final temperature. So, we have 0 minus, what is the initial? We have 25. So, both these quantities are expressed in degrees Celsius. So, we factor out the degrees Celsius. This will cancel out. So, negative times negative, that will give us a value of positive. And 25 times 2 will give us a 50. Negative 2 millivolts times 25, that will give us a 50 millivolts. Or this is simply equal to 0.050 volts. So, what is now the barrier potential when the temperature decreases? Remember, it decreases. So, what do we expect? We expect that the potential difference, barrier potential will not increase. I will increase. Okay, will increase because your temperature decreases. When your final temperature increases, expect a decrease in the barrier potential. So, our barrier potential before it was 0.7 volts. Then we're going to add the change. What is the change? We have 0.050 volts. Or simply this becomes, .705 volts. So, what did you observe? So, it simply follows that this is now 0.75. So, it simply follows that there is an increase of barrier potential when your final temperature decreases. There is an decrease of barrier potential when your final temperature increases. So going back to the principle that was explained earlier, as I said here, the barrier potential of a silicon diode decreases. No? The barrier potential decreases. This only happens if there is a rise or increase. So, for that reason, going back here, there is a rise of temperature. So, therefore, your barrier potential of the diode decreases. If there is a decrease in temperature, therefore, the barrier potential of your diode increases. So, thank you. That is now the relationship of the barrier potential and temperature for a silicon diode.